Okay, so this video is to run through some basic graph transformations. So I'm starting with my original graph which is this. So I've called it y equals f of x. It happens to be y equals sine of x. So it goes from 1 to -1 and repeats every 360 degrees. However, the fact that it's sine x is kind of neither here nor there in terms of the generalizations we want to make about graphs and transformations, because the things I'm going to say in this video should apply to any graph. So I'm going to look at y equals 2f of x. So taking the function and multiplying it by 2. So in the particular case of sine x, that would be the graph of y equals 2 sine x. But as I say, that's neither here nor there really. We're just interested in generalizations about what transformations do to graphs. So I'm just going to zoom in on this. I'll just trace it out, and then I'm going to stretch it a bit. So multiplying all of the values by 2 will make them all 2 bigger. So everything stretches away from the x-axis and increases by a factor of 2. So I can write, I'll just get rid of this that I wrote here. So my description of that transformation, I'm going to call that a vertical stretch scale factor 2. Okay, the next function is y equals f of 2x. So this is where you do something to the x before you apply the function. So in this particular case, it would be y equals sine of 2x. So you can go ahead and graph this on GeoGebra if you like. But what you need to remember about these generally is if you're doing something to the x first, let me just trace out the original again. Okay, so if you're doing something to the x first, then it has a horizontal effect on the graph, and what it does might be counterintuitive to what you were expecting. So it actually squashes it up so it's half as big as it was in the horizontal sense, and then I can just kind of copy one of those and paste another one if I can figure out how to do that. Paste another one of those there because it sort of repeats like that. Yeah, so you get something that instead of repeating every 360 degrees as the original did, repeats every 180 degrees. In fact, I should have squashed that up a bit more, shouldn't I? Repeats every, there it goes, 180 degrees. Just get rid of that one and then copy and paste that one. There we go. Just paste another one, I think. Yeah, so you get the idea of that. So I'm going to call that a horizontal. Well, I'm going to call it a stretch, even though it's not really stretching. It's more like it's squashing it. But I'm going to call it scale factor a half to reflect that fact that it's actually kind of squashing in. Okay, here comes the next one, f of x plus 1. So for example, that would be y equals sine of x plus 1. So if you're adding 1 to all the values, then they're all just going to kind of shift up by 1. So again, I'll trace out my original. So all that's going to happen to that is the whole thing is going to get shifted up by 1 unit as all of the values increase by 1. So we can call that a translation. If you want to use baby language, you can say 1 unit up, or you can say by the vector 0, 1. That is to say, it's going 0 units left to right and 1 unit up. Okay, the next one. Y equals f of x plus 30, or f of brackets x plus 30 close brackets. So for example, that would be y equals sine of x plus 30. So once again, when you do something to the x first, it's going to have an effect in the horizontal plane rather than the vertical plane, and that effect might be counterintuitive to what you were expecting. So I'll just trace this out again. So because of the plus 30, you might expect it to go that way by 30 degrees, but actually it goes to the left by 30 degrees. So you can go ahead and verify this in GeoGebra by plotting the whole thing out, but you can just remember a generalization that that is going to be a translation again, because the whole thing is just moving without changing shape. So you can say 1 unit to the left, but you can also say it's 30 units to the left, I should say, because it's 30 degrees. 30 units to the left, but you can also express that in terms of vectors. So it's a translation by the vector minus 30, because it's going 30 backwards, if you like, if you think of to the left as being backwards, and then it's going 0 up or down. And the next one is kind of the same idea, so I'll just zoom in once more and trace that out. Not very well. Let's try again. Okay, so f of x minus 30. So again, it's going to be in the horizontal plane when you do something to the x first. But in spite of it saying minus 30, it actually goes in what you might think of as the positive direction, but to the right. So once again, that's a translation. And it's a translation by the vector 30, 0. It's gone 30 across to the right, and then 0 up or down. Okay, y equals minus f of x. So all of the plus values are going to become the minus of what they were, and all of the minus values are going to become the plus of what they were. So what that is going to do, I'm just going to plot out a few key points that this is going to go through. So it's just going to kind of flip the whole thing. There. Could have drawn that better, but you get the idea. Just delete that. Okay, so it's just going to flip the thing in the x-axis. So you can call that a reflection, if I can remember how to spell reflection, in the... So you can call it the x-axis, but remember that the x-axis is also the line y equals 0. So reflection in the line y equals 0, if you like. And then once again, doing something for the next question, doing something to the x first has an effect in the horizontal plane, and it's kind of the opposite of what it does in the vertical plane. So what that does actually is reflects it. I can't quite get the thing to fit on, unfortunately, but it's going to be a reflection in the y-axis. So it's going to be a reflection in that line, so it's going to sort of go up there. But then, of course, the sine graph carries on forever in both directions anyway. So it's actually going to look the same as the reflection in the x-axis. But this particular one, because it's minus x first and then apply the function, it's actually a reflection in the y-axis, also known as the line x equals 0. So once again, remember, the y-axis is the line x equals 0 because of all the x values being 0 on any points on the y-axis, and vice versa for the x-axis being the line y equals 0. Okay, moving on. So this time we're looking at some quadratic graphs. So this is the original function. As it happens, it's the graph of y equals x squared, but that should be neither here nor there to you, because the same general rules about transformations are being applied. So if I just go back to red here. So that's my original function, and doing plus 3 just means that all of the values are 3 more than they were, so the whole graph shifts upwards by 3 units. So again, that's a translation. You can say 3 units up, or you can actually write a vector translation by 0 units across and 3 units up. Next one, y equals f of x plus 2 in brackets. So that is going to be something that shifts the original graph. Let's just get my pen on there. Try and draw that a bit better. Okay, so again, you might intuitively think it's got to go to the right for plus 2, but it's got to go to the left, so that it has an apex, if you want to use the proper name for that, at the point minus 0, 2, and it's a translation, so you can say 2 units left, translation 2 units to the left, or you can refer to the vector that it's changing by, so minus 2 for 2 backwards to the left and 0 up or down. And the next one is, of course, the same idea. So you've got your original function. Let's just trace that out quickly. So that's y equals f of x, the original, then doing minus 4 to the x first before applying the function. We'll shift it to the right by 4 units. So again, that's a translation. 4 units to the right, or in other words, it's by the vector 4, 0. Okay, moving on to the next one. Y equals minus f of x. So that's just all of the values being the negative of what they were. So that's just going to reflect everything in the x-axis, and then the whole graph will get flipped upside down in the x-axis. So that is a reflection in the x-axis, which is also known as the line y equals 0. So once again, remember that the x-axis, the equation of it is the line y equals 0. Right, the next one, y equals f of minus x. So we're doing something to the x first before we're applying the function. So what happens there is it actually just reflects in the vertical axis. So those should look the same if I'd drawn them better, but it's just a reflection in the vertical axis. So reflection in the y-axis, and the name of the y-axis is the line x equals 0. You can also talk about the line that it reflects in being called the axis of symmetry. Okay, next one, y equals 2f of x. So all of the values are 2 bigger than they were before. So everything gets 2 further away than it was from the x-axis. So it's just getting stretched out by a factor of 2. So you can call that a vertical stretch, if you like. Scale factor 2. Now, if you do f of 2x, then it's going to squash it by a factor of a half horizontally. So you're going to get kind of the opposite thing to maybe what you were expecting, and in the horizontal plane. Horizontal, so I'll still call it a stretch, but it's going to be scale factor a half. So if I take the original graph and trace it out, see if I can do that in one thing. It's going to look a bit like this, where it gets squashed up, so everything's half as far away as it was from the vertical axis compared to before. Now, of course, that doesn't look much different from the one where you stretched it vertically, so be aware that they're quite similar looking. Okay, next one. So now it's applied to some actual quadratic functions. So there's the original y equals x squared, and we want to do y equals x squared minus 3. So that's just shifting it down by 3 units. 1, 2, 3, down by 3 units. It's a translation by 0 minus 3. Okay, y equals x plus 1 all squared. So we're adding 1 to the x before we're applying the function, and that has the effect of shifting the graph horizontally, not in the direction of plus 1 as you might expect, but counterintuitively perhaps the other way. So that's going to be a shift of 1 unit left to the left. So translation 1 unit to the left, or in other words, minus 1, 0, 1 back, 0 up or down. Next one is very similar to that. So you're subtracting 2 from the x before you're squaring it. So that's just going to take the original graph and shift it to the right by 2 units. So it's a translation 2 units to the right, i.e. a translation by the vector 2, 0. On to the next one. So this is one now. This is more likely what you might see in an exam. So I've got my original function, and then the +2 there is going to shift it 2 units, not to the right, but to the left. And then the -5 there, that -5, is going to make it go 5 units down. 1, 2, 3, 4, 5. So it's going to bottom out here at the point -2, -5. Bear in mind I'm not using the same scale horizontally as I am vertically. Different numbers of squares for 1 unit. Okay, so that's a translation. So it's gone 2 units back and 2 units down. It's a translation by -2, -5. Everything's gone 2 to the left and 2 down. Right, and then there's this one, y equals x squared plus 2x minus 4. So the idea is that we want to write it in this kind of form so that we can break it down into a movement left or right and a movement up or down. So the trick to that is to look at the equation, look at the coefficient of x, which is in this case 2, halve that and square that. So you do all that. In this case it gives you 1, which means that we want to write this -4 as something involving 1. So I'm going to rewrite that as y equals x squared plus 2x. Then instead of -4, I'm going to write +1 minus 5, so that it's something involving the 1. Now the point of doing that is that this bit here becomes a perfect square. So that bit there is a perfect square of x plus 1 times x plus 1. You can see that from 1 times 1 makes 1, x times x makes x squared, x times 1 plus the other 1 times the other x makes 2x, so it's a perfect square. So that whole bit in the middle can be written as x plus 1 times x plus 1, and then don't forget the -5 that was on there, and x plus 1 times x plus 1 I can just write as x plus 1 squared. So the whole thing can be written as x plus 1 squared minus 5, and once I've got it written like that, then I can just take the whole thing and realize that it goes 1 unit to the left for the +1, and then 5 units down for the -5. So it's going to have an apex at -1, -5, and the whole thing is a translation by the vector -1, -5. It's gone 1 unit back to the left and 5 units down. Okay, so the last 2 questions, the same sort of idea applies to that. So if you understood that, maybe you want to pause the video and just work through the last 2 on your own. So just a little opportunity for you to pause there. Otherwise, let's go ahead and do it. Okay, so x squared minus 6x plus 2. I want to look at the coefficient of x, which is minus 6, halve it, which is minus 3, square that, which gives me 9. So I want to rewrite the whole thing involving a 9. So instead of x squared minus 6x plus 2, I'm going to write it as x squared minus 6x plus 9 minus 7. So I'm rewriting the 2 as 9 minus 7 so that it involves a 9. Having done that, then this bit in the middle comes out to be a perfect square. So it's perfectly x minus 3 squared. And by the way, the number here is always just going to be half of the number here. Okay, so x minus 3 squared, and don't forget the minus 7. And having written it like that, that helps me realize that it's going to be like the original graph, but the x minus 3 squared is going to take it 3 units to the right, and then the minus 7 is going to take it 7 units down. 1, 2, 3, 4, 5, 6, going off the page, 7. So that it has an apex down there at 3 minus 7. And then the whole thing is a translation by the vector 3 minus 7, because everything's gone 3 to the right and 7 down. Okay, last one, same idea. So half the coefficient of x squared is 4 over 2 squared, which is 4. So I want to rewrite the whole thing involving a 4. Y equals x squared plus 4x. So instead of 3, I'm going to write plus 4 minus 1. Then this bit comes out to be a perfect square. Y equals x plus 2 squared. And then don't forget the minus 1. Again, this number here is always just going to be half of this number here. Okay, so now that I know it's x plus 2 squared minus 1, I can just take my original graph and say, okay, so the x plus 2 squared bit is going to make it go 2 units to the left, and then the minus 1 is going to take it 1 unit down. So it's going to have an apex here at minus 2 minus 1 coordinate, and then the whole thing is a translation by the vector minus 2 minus 1, written like that, to say that it's gone 2 back and 2 down.